as unfortunately pretty much everyone is aware these days, Alzheimer's is a pretty devastating neurodegenerative disease. And this is what Alzheimer's looks like in the brains of a patient at autopsy. What you're looking at here are so-called neurofibrillary tangles. These are deposits of a protein called tau, build-up of protein called tau in the neurons, in the actual brain cells. And what happens whenever this protein builds up and sticks together and has abnormal modifications happen to the protein, we get what are called neurofibrillary tangles. And neurofibrillary tangles are not only a hallmark of Alzheimer's disease, they're also a hallmark of traumatic brain injury, and I will come back to that later. This is the other key pathological feature of Alzheimer's disease, the so-called amyloid plaque, or senile plaque. Amyloid is a small protein that we all make all the time. It's got some normal role in our development and our function because it's been highly conserved throughout evolution. We all make it normally, so it does something normally, and research that we've carried out here at the Institute suggests that it may have a role in blood vessel maintenance. But whenever we get older, or if we have mutations that cause early onset Alzheimer's disease, one of the things that happens is that instead of amyloid moving out of the brain after it's done its job, it builds up. And as amyloid starts to build up in the brain, it starts to become insoluble. And so it starts to come out of solution and form these plaques. This is an amyloid plaque, which is an extracellular deposit of this protein. Now, amyloid is pretty central to everything I'm going to talk about in the Alzheimer part of my presentation today, because that's what we have really focused on at the Roskamp Institute. Dr. Mullan, the director of the Institute, he and I were part of the team in London that 20 years ago identified the first genetic cause of Alzheimer's disease. And those genetic causes were mutations in the amyloid gene. Now, just for the sake of the non-scientists in the audience, I'll just very quickly tell you that our genes encode a message that results in the proteins that our bodies are comprised of. So when you get a genetic error at the DNA level, then that can result in a change at the protein level. And that molecular level of analysis is fundamental to everything that we do here at the Roskamp Institute. This schematic is probably a little bit difficult to see. I apologize for that, but the pink here represents the full-length amyloid precursor protein. And this piece here is the amyloid protein that is cut out of that larger piece. And this is the piece that causes the problems in Alzheimer's disease. And I won't go into all the details here, but suffice to say there are several different ways that this larger protein can be cut up. One of the ways means you don't get amyloid being formed at all. But if you go to the right here, this direction, you get amyloid being produced. And the mutations that we found, and that other people have subsequently found, that cause early onset Alzheimer's disease, all result in an increase in production of amyloid. So if you picture, just to make a mental picture of that, the one I like to use is if you think of adding sugar to a glass of water. When you first start adding sugar into a glass of water, it goes into solution and you don't see it anymore. But if you keep on keeping the sugar in, it starts to settle out on the bottom. And that's how you can picture what happens with amyloid in the brain. As too much of it starts to be produced and not enough of it is getting cleared out of the brain, then it starts to come out of solution and stick together. And that's when we see those amyloid plaques.